So we have discussed in the last video and in previous sections how to find a first derivative, dy dx, the slope of a parametric curve. And I briefly mentioned how to find a second derivative now, which we would use for concavity. Uh, and so to use an example here, here we have a parametric function. I use my calculator to help me sketch the curve and get an idea of its direction. So it's coming up kind of like this, and it's going this way. And it's nothing fancy, again, it's just a sketch. But to find the highest point, what we're really saying here is we want to maximize y. Well, to maximize y, that means we're looking at dy dt. If I wanted to find the furthest right point, that would be maximizing x, so I would use dx dt. If we're finding the furthest left point, that'd be minimizing x, still dx dt. If I wanted the lowest point, that's minimizing y, I want dy dt. But I want the highest point, so I'm maximizing y, which means I would look at the endpoints. This is going back to when we were doing optimization with our derivatives, which I believe was chapter 5. Uh, and at our endpoints, t would be 0 or pi. So when t is 0, y is 0. When t is pi, y is also 0. So those are not looking very good for our highest point. The other place I would then check are critical points, and for that I need dy dt. Well, dy dt would be 2 cosine t. That is never undefined. However, dy dt would equal 0 when pi equal, when, oops, I would be using t equal to pi over 2, which is the only value between 0 and pi that would happen at. And checking my sign chart from 0 to pi over 2. Now I'm checking dy dt. From 0 to pi over 2, like pi over 4, dy dt would be positive. Something like 3 pi over 4, dy dt would be negative. And so I am seeing that there's going to be a maximum for y at pi over 2. And so when t is pi over 2, uh, the y would be 2, and my x would be pi squared over 4 minus 5, whatever that value is, as a decimal. If I wanted to find points of inflection, this requires using the second derivative. So the first thing I would need is dy dx, which is dy dt over dx dt. Well, dy dt, as we already found for finding the highest point, would be 2 cosine of t. And dx dt would be 2t. Well, again, that's my dy dx. I need d squared y dx squared for concavity, which is what I need to see where it changes. And so for this, I would take my derivative of dy dx with respect to t over dx dt. So to do derivative of dy dx with respect to t, I'm going to need to use quotient rule. So that's bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. And just to make this look a little bit nicer, be negative 4t sine t minus 4 cosine t all over 4t squared. And I'm interested to know where does this 0 and where is it undefined. Undefined at 0, which is an endpoint, so that's not going to be a point of inflection. To see where this equals 0, so my second derivative equals 0. I need to see where negative 4t sine t minus 4 cosine t equals 0. And I went ahead and solved this on my calculator, and I got that t is 2.798. And actually on my calculator I can see this is a graph of my second derivative here, and I can also use that on my sine chart. So 0 to 2.798 to pi, and this is for the second derivative, d squared y dx squared. And from 0 to 2.798 I can see it was negative, and then from 2.798 to pi is positive. And so my concavity is changing from concave down to concave up because my second derivative is changing signs. So I do have a point of inflection when t is 2.798.